Today on Macaulay Math, we're talking properties of logarithms and modeling with logarithmic functions. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 13 on logarithmic functions. Our goals for today. We're going to rewrite logarithmic functions with different bases. We're going to use properties of logarithms to evaluate and rewrite logarithmic expressions. We're going to use properties of logarithms to expand and condense logarithmic expressions. And finally, we're going to use logarithmic functions to model and solve problems. In this lesson, we will discuss both the elementary properties of logarithms and the change of base formula. Additionally, we will discuss the property of logarithms that allows you to change an exponent into a multiplication. This property will be used extensively over the next few lessons to solve equations where the unknown value is an exponent. Let's get started.
Okay, so let's start with these properties of logarithms, and the first two properties of logarithms allow you to manipulate logarithms in a specific way. Now, to be perfectly honest, you're going to find these first two properties far more useful in calculus, but this is a good place for us to introduce them. And basically what they say is that if you have a logarithm of two different values or expressions that are multiplied together, you can separate them into two logarithms separated by an addition. So a simple example of that would be for me to say, okay, we're going to take the ln of 3x, and we can rewrite that as the ln of 3 plus the ln of x. Now that may seem weird that you can separate a multiplication and change it to an addition, but remember the definition of logarithm relates logarithms to exponentials, and so this property of logarithms is related to the property of exponents, where you go if x to the a times x to the b is equal to x to the a plus b. And so you can see multiplication and addition are related similarly in this fashion. Now this second one takes a division and separates it through a subtraction. So again, a simple just common logarithm of 4 over x can be rewritten as the common logarithm of 4 minus the common logarithm of x. This last property of logarithms, this one right here, this is the one that we are learning logarithms for in this unit. And what it allows us to do is to take this exponent and bring it down in front and make it a multiplication. And so what it's going to allow us to do is to solve that equation where we had 10 equals 3 to the x. We want to know what x is with some accuracy. And this property is going to allow us to do that. The change of base formula is a formula that allows you to calculate a logarithm of any base. And the reason I bring it up here, and even though it's simple, and Desmos actually allows you to calculate logarithms of any base fairly easily, the change of base formula is a nice little example of this third property and allows us to do a nice little exercise that derives the change of base formula. So what we're going to do is say, what if I wanted to calculate log base 3 of 5? All right, let's say I wanted to do that. Now, let's do it in general. Let's write that in general and say that it is log base a of x. So I want to calculate something of this form where I don't have that base as a logarithm. We can take this log base a of x and set it equal to y, and then use the definition of logarithm and rewrite it. So we'll go a to the y is equal to x. And remember, we're solving for y. And so here, I'm going to say, take a known, I'm going to put this in parentheses, I want I say a known logarithm, it's something that's calculable. So most scientific calculators have the common log, log base 10, and the natural log, ln, which is log base e. And so if I take a known logarithm of both sides, and let's say I'm going to take ln and go ln of a to the y is equal to ln of x. Now, you guys have all been solving equations since probably 5th or 6th grade using algebra properties, and you know that if you do the same thing to both sides, your equation stays balanced, and logarithms are no different. And now, because I have this logarithm here, I can bring this y down in front. And so I can use that property and bring that exponent down front. I can bring that y down front and rewrite that as y times the ln of a equal to the ln of x. Now, ln is on our scientific calculator, so we can calculate whatever that value is, provided we know what a is. And since that's a calculable value, I have y times a. So to get y by itself, I'm going to divide both sides by ln a. And what that does is y equals the ln of x over the ln of a. And so now I have a new formula that calculates a logarithm of this form. If I know what the value of x is, I know what the value of a is, I can plug in that x and that a and just divide those two logarithms to calculate that value. That is the change of base formula. The change of base formula basically says if you have a, b, and x be positive real numbers, such that a is not equal to 1 and b is not equal to 1, then log base a of x can be converted to a different base using any of these equivalencies. We calculated this equivalency, but we could use common logarithm as our numerator and denominator, or we could use any known logarithm as our numerator and denominator base. And again, since most scientific calculators have common logarithm and natural logarithm as known logarithms, you can do that calculation anytime you want. As an example, it says rewrite the logarithm as a ratio of common logarithms and as a ratio of natural logarithms. This is the ratio of common logarithms and this is the ratio of natural logarithms. Since we have a value for x and a value for a, this is actually a pretty easy problem. We can say that this is the common logarithm of 7 divided by the common logarithm of 3. That is my ratio of common logarithms. And if I want to do the same thing with natural logarithms, I'll go ln of 7 over the ln of 3. That is my ratio of natural logarithms. This is my final answer for that problem. The next example asks us to actually evaluate using the change of base formula, and we're allowed to do that with any known logarithm. So just to keep it simple for me, I am going to rewrite this logarithm as the ln of 6 over the ln of 4. Now Desmos lets us do this in a number of different ways. So let's go to Desmos. And Desmos allows us to just type in the logarithm. So if I just type in ln 6 divided by, and then I hit that backslash for my divided by, ln of 4, it will make that calculation for me. So I can do that. Now, Desmos also has a change of base formula in it. So if you pull up the keypad and you go to functions and then you scroll down, almost all the way to the bottom, you'll get to calculus where you have log base a. And so here, if I click that log base a, it gives me that subscript, so I can type in the 4 and I can type in the 6 and that will give me that same logarithm. Or if I go log and then I hit shift and then I hit the underscore button, that'll push it down into a subscript with a 4, and then I can put it up top and enter a 6 and still get that same value rounded to 3 places will be 1.292. So this is 1.292, and that is my final answer for that problem. All right, next it says use properties of logarithms to expand the expression as a sum, difference, and or constant multiple of logarithms. So basically what they're asking us to do is use these first three properties of logarithms to break this expression so that it's a logarithm of only one variable and it has no exponents in that logarithm. So for this first one, I am going to use that property of logarithms, log base a of x times y is equal to log base a of x plus log base a of y. And what that's going to allow me to do is separate this into log base 2 of x squared plus log base 2 of y to the third. Now that I have this expression, I can use that third property of logarithms that says log base a of x to the n is equal to n times log base a of x. And I can use that to bring both of those two exponents down in front. So I'll have 2 times log base 2 of x plus 3 times log base 2 of y. And now I expanded the expression as a sum or difference. There's my sum, and a constant multiple of logarithms. 2 and 3 are constants that are multiplying the logarithms. In this second example, we do have to, before we can move forward, recall that a radical can be rewritten as a rational exponent. So the square root of x can be rewritten as x to the 1/2 power. And so I'll do that first. So I'll go log base 4 of x to the 1/2 over y to the 4th. Now this one's going to be similar to the last one, except we're going to use the property where it says log base a of x over y is equal to log base a of x minus log base a of y. And so I can use that to separate into two logarithms. I'll have log base 4 of x to the 1/2 minus log base 4 of y to the 4th. And then we'll bring those exponents down using log base a of x to the n is equal to n log base a of x. And I'll bring both of those exponents down. I'll have a half times log base 4 of x minus 4 log base 4 of y. We'll put equal signs at each step, put a box around my final answer, and we will call that done. In these next two examples, we are condensing the logarithms, and so we're basically doing the opposite of what we did in the last two exercises. So we're going to take multiple logarithms with constant multiples and we are going to push them together using the rules. So we're going to work backwards. So in this particular one, before I can condense the two logarithms that have a minus, I have to push my exponents back up. So here we're going to use log base a of x to the n equal to n log base a of x, except we're going to use it in reverse. We're going to go this way. And that will give me the ln of x squared minus the ln of y to the 4th. So I'm just pushing that up into an exponent, that up into an exponent. And then we will use log base a of x over y equals log base a of x minus log base a of y. And again, we're using it in reverse. Since I have a minus, I can condense that to a single logarithm with a division and rewrite this thing as the ln of x squared over y to the 4th. Put a parenthesis around that, box the whole thing, and that one is finished. Similarly here, you'll notice that I have no constant multiples in front, so I can go right to the property of logarithms that says log base a of x times y is equal to log base a of x plus log base a of y, and we will push them together. Again, we're moving this way. So we're condensing from 2 logarithms to a single one. Since it has an addition here, we can condense it with a multiplication and say log of x plus 1 times x minus 2. And here we should simplify this. And we'll do that by distributing. And when I distribute, I still have my log. And then it'll be x times x is x squared. X times negative 2 is negative 2x. 1 times x is 1x. Plus the negative 2x is negative x. And then 1 times negative 2 is negative 2. We'll put a box around that, and we will say that that is our simplified version. Last set of examples, it says evaluate the logarithm without using a calculator. So the first thing we're going to do is we'll set this equal to y. We want to evaluate it without a calculator. And then we will use the definition to convert that to an exponential. So I'll have 3 to the y is equal to 81. Now the only way I can do this without a calculator is if 81 is a perfect power of 3. And I will recall that 81 is equal to 3 to the 4th power. So 3 to the y is equal to 3 to the 4. And if the bases are the same, then the exponents are the same. So we know that y must equal 4. We'll put a box around that and say that that is correct because we are trying to evaluate this expression, which we set equal to y. So similarly, I'm going to set this one equal to y, and we'll use that definition of logarithm. So 5 to the y equals 1 over 125. And again, we want to be able to do it without a calculator, so the only way that works is if 125 is a power of 5. In fact, 125 is equal to 5 to the 3rd. So I can rewrite that as 5 to the y equal to 1 over 5 to the 3rd. And then we will recall the property of exponents that says x to the negative a is equal to 1 over x to the positive a. And we'll use that in reverse. So we'll take this positive exponent in the denominator and rewrite it as a negative exponent in the numerator. So 5 to the y equaling to 5 to the negative 3. And therefore y equals to negative 3. All right. Well, that's all I got for today, folks. So, Star Wars fun fact of the day. George Lucas's first choice for the voice of Darth Vader was to be Orson Welles. But he thought that the famous actor's deep, resonating voice would have been far too recognizable, and therefore he eventually set on James Earl Jones as the iconic voice. Well, that's all I got for today, folks. Have a great day. Goodbye.